Hello. Today I'm going to be discussing Cayleys' theorem, which is a topic in abstract algebra, under the topic of group theory. So as Boris previously mentioned, Cayleys' theorem just states that every group is isomorphic to a permutation group. So we're going to delve into why that is. So just a bit of prerequisite knowledge. So a group is just a certain type of set which follows a certain set of axioms. These axioms are as follows. So we have the associative axiom. Two, we have the closure axiom. Three, we have the identity axiom. Four, we have the inverse axiom. Sorry for my poor handwriting. So we're going to discuss these as we go along in the proof. So let's get started with the proof. We're going to start by making the claim, let big G be any group and let little g be an element of big G. Cool. All right, we're also going to define TG as mapping G from G to G. So, and we're also going to state the prerequisite rule that Tg of x is equal to Gx. That is going to be important. So we're going to first show that it is injective. So by doing that, we are going to show that Tg of x is equal to Tg of y. Now, by this rule up here, we know that Gx is equal to Gy, and by left-hand simplification, we know that x is equal to y. We've now proved that it's 1 to 1, and that proves that it's injective. That's a big check mark there. Now we're going to prove that it's surjective. So, we have the inverse law, which states, well, let's first name some prerequisite. So y is an element of G, and because of the inverse, G inverse times composed with y is also an element of G. So Tg of G inverse of y is equal to G from up here times G negative 1 times y, and we know that this will go away. That's just equal to y, and now we have proved that it is, together we have proved that it's bijective, which is important. Bijective is another way of simply stating that it is a group. All right, so it's a subgroup. So let's make a new whiteboard here, and I'm going to pause first. So right now we are going to describe the fact that the set of all TGs will be its own group. So let's define G prime, which is going to be equal to all of the T of G's given G is an element of G, big G. Okay, so we're going to make the claim, that G prime is, in fact, a group. We're going to have to prove that. How do we prove that? Well, we're going to prove that by saying, I'm going to prove this claim by proving it follows the given axioms. Well, how do we do that? Well, let's gonna make a new whiteboard here. Okay, let's start with the identity axiom. So for the identity axiom, let's say that TG in parentheses composed with TE. Now E is going to take the place of the identity and multiply or composed with X. Now we're going to see that that is just going to become TEX. And since E is just the identity, it's going to be equal to not an X, that's a G. TG, which is just equal to I made a bit of a mistake here. As we proved, or as we showed earlier, this is actually, GE of X. And GE of X is just equal to G of X, given GX, because E is our identity, and the identity is just what you multiply to get ideally the same thing. GX is also equal to TG of X, which has proven our identity. So that's a big check next to the identity axiom. Now let's prove the inverse axiom. So we're going to say that G inverse is the inverse of G element big G. And that T inverse G is the inverse of TG in G prime. Thus, TG inverse composed with TG is equal to TG inverse time composed with G, all in there, and TG composed with TG inverse is equal to TG G inverse, which is just equal to T of E, which is our identity axiom. Okay, so that's two axioms, and then the other two axioms, for time's sake, I am not going to discuss. However, they are relatively simple to prove. Very simple. So I'm going to make a new whiteboard, and we're going to get into the meat of the proof now, well, the real part of it, where we've already determined that G prime is equal to TG. G is an element of big G. Sorry about that. However, we're now going to prove that normal big G is, in fact, isomorphic to G prime. That is the big part. That is the big part of this proof. Okay. Okay, so now we're going to consider a map. Shoot, that looks too much like an integral sign. For phi, wow, I cannot draw phi. Sorry, I wrote it out. So phi is a map of G to G prime, where phi G is equal to T sub G. So that is our prereq. So to start, we're going to compose a group law in which we state that phi of two arbitrary GH is equal to T sub GH. Now we know that's true because of our previously mentioned law. So now we're going to note that TGH of X is equal to GHX. that's also just equal to T sub G composed with T sub H, all composed with X, which is also equal to phi of G composed with phi of H composed with X. This is thus showed us that phi of GH is actually equal to phi of G composed with phi of H, which is a very important part. Okay, so now that we've proven the group law works, I'm going to create a new whiteboard here. We are now going to show that it's injective. And due to the definition of G big G prime, we don't actually need to prove that it's surjective. By its definition, it automatically is. It's just surjective. So if we can prove that it's injective, we prove that it's bijective. And in doing so, we prove that G prime is actually isomorphic to G, and that finishes our proof for us. So that's our roadmap. So let's get started with the injective proof. So we're going to suppose or assume that phi of G is equal to phi of H. We're also, because of our previous rules that we came up with, we're also going to define that T sub G is equal to T sub H, because we know that the phi and the T are equal. We know that two functions, so T sub G and T sub H, are only the same if they completely agree within all given numbers within the domain. So we'll have T sub G of X is equal to T sub H of X. So in particular, this only needs to be true for X is equal to the identity E. Now, if we notice, if X is equal to the identity E, then T sub G of X is just equal to G. And then if we take T sub H of X and we make that same assumption that X is equal to the identity, then we just have that it's equal to H. And if we take this preset and put it over here, that just gives us that G is equal to H for all element G, which does formally prove that G prime is, in fact, isomorphic to G, which G prime is a subgroup, which thus proves Cayleys' theorem. It's a very complicated proof dealing with some advanced group theory ideas. However, that is how it ends. Okay.